All right, here are the notes for 6.8. And then when we're done with 6.8, you can pause it so you can study for the quiz for 6.6 and 6.8. And then, or you can just keep playing it because 6.1 will be after. 6.1 will be attached to chapter 10, I believe. Okay, so this is a warm-up in 6.8 for coordinate geometry. And if you look at the blank version, it might make more sense. And so you're given 3 points A, B, and C. It says how many, what are the possible coordinates for point D to make a parallelogram? Okay, so there's actually 3 possible answers. All right, 6 comma 0 is a blue rectangle here. Okay, if you try to ignore the yellow and the red. Negative 4, 4 is, if this were D, where right here where I'm highlighting, right? D, B, C, A makes this parallelogram, okay? And then here in red, 8, 6, all right, you have D, C, A, B up here, okay? This red parallelogram, okay? Because as it says here, all of these would form opposite sides that are parallel and congruent, all right? So, some of this stuff might seem confusing because we're not really using numbers for the coordinates, but we're going to use letters. Okay. Read over what it says here in terms of naming a coordinate. All right. And so here, the origin is 0, 0, right? In example 1, it says SOTW is a rectangle. And so this is why you got to know the properties of all of the different shapes, all right? If O is at 0, 0, and look at here, if S is 0h, that means the height is h, right? Because it's 0h. And the y value, the second number, represents the height. If this is B0w, right? That means the distance from 0 to w is some length b, right? Then that must mean that point T is b comma h, right? And again, same thing with sides here, right? For a square, we know that all sides are congruent, and so if each length is a, then T must be a comma a, all right? Okay, and so with the rhombus also, right? We know a rhombus, all sides are congruent, all right? And they also tell you that SW is 2R, so that means, remember, diagonals of a rhombus bisect each other. Okay, so that means the 2R gets split to R and R, the 2T gets split to T and T, and so therefore you have these coordinates here. Okay. In an isosceles trapezoid, it says the base is centered at the origin. That's key, right? If it's centered at the origin, then it splits this base in half, right? Same with the top base, okay? So therefore, from 0, this is out to A, and this is out to negative A, right? So that the total distance is going to be 2A. And up here, the total distance is going to be 2B, all right? It says OR is C. So from the origin to this point R is C. Well, this height OR is the same as this height up to W and also to T, right? That's why we have BC and negative BC over here. Okay, and so same ideas here with trapezoid and kite. All right, trapezoid with a right angle, that's key right here. Okay, look those over. And using variable coordinates. Okay, example 7 says, without using any new variables, what are the coordinates of B? All right, you can pause here and try it, or pause it and take a look and, think about it. All right. Okay, same thing here. Okay. Here, with the parallelograms and the isosceles trapezoid. All right, what are the coordinates of L and what are the coordinates of P, right? This is going to be A plus C for L, right, for the first number, the X coordinate, because if this is A, right, and if from 0, from 0, 0 to M, if that whole length is C, right, and from 0, 0 to here, if this is little a, well, that's going to be the same amount here. So this is M, right? This is, a length of C, and then plus A. That's why this is, or A plus C, I guess. All right. And so, yeah, let me go back here, okay? If you need to rewatch or go over these notes for 6.8, please do, because the next part is 6.1, and that will not be part of the quiz. So if you want to pause here and look over your notes for 6.6 and 6.8, you can do that, and then start rewatching the video for 6.1. All right, in 6.1, we're going to start looking at different polygons, all right, different shapes. And the first thing we're going to look at is the sum theorem of polygon, all right? And so if we were in class, I would have had you, fill out this chart, and it would have been a good discovery activity, okay? You got to know these names, by the way, all right? We know a triangle is a three-sided figure, quadrilateral is a four-sided figure, and so on and so on, okay? So you got to know these names here, all right? And this last column, the sum of the measures of interior angles, meaning if you were to add up all of the angles inside of that shape, what do they add up to? All right, so the number of triangles inside, okay, I'll explain that in a second, okay, and so there's a formula here for any polygon. You can figure out the sum of all of the angles inside. Okay, so here I drew a heptagon for you. This is a seven-sided figure, right? And the number of triangles, well, that's from, if you pick a corner, right? Just any corner, I guess, okay? Or what's called a vertex. How many, well, I'm going to draw all my diagonals, right? I can draw this diagonal. I can draw this diagonal. I can draw this diagonal. And I can draw this diagonal right here, right? Okay. Well, there are 1, 2, 3, 4, 5 triangles within this heptagon, right? And, well, in one triangle, we know that the angles of a triangle add up to 180, right? And so if there are 5 triangles, then it's 180 times 5, right? Which comes out to 900, okay? And so that's why there's this formula here, right? The n minus 2 represents the number of triangles within a polygon, right? The 180 represents how many degrees there are per triangle, okay? So the n minus 2 is the number of triangles, and the 180 is the number of degrees, okay? So that's what this whole activity is, all right? Okay, so that's the theorem here, the polygon angle sum theorem. Okay, a couple examples here. Find the sum of the interior angle measures of each polygon. So for a 36gon, meaning 36 sides, okay. I think we're using SI for the sum of the interior angles. It's 36 minus 2, so there are 34 triangles, and then times 180. A couple vocab words here, all right. Equilateral, we know that all sides are congruent. Equiangular mean all of the angles are congruent, okay. And putting that together is what we call a regular polygon, all right. This is a new vocab word that you're going to have to know. So whenever you see this word regular polygon, it means that all the sides are congruent and also all of the angles are congruent. They're equiangular. All right, so that's what a regular polygon is. All right, probably the most basic one that you know is a square. Right, a square is a regular polygon because all the sides are congruent and it's equiangular because all of the angles are 90 degrees. All right. Here's an example. If you look at the notes, all right, find the missing angle measures. First, you got to know that this is a five-sided figure, right? It's a pentagon, okay? And so you got to figure this out first. You got to figure out, well, what do the angles add up to in a pentagon? All right, so it's 540. And so now you can do this setup. If you add all the angles, it's going to equal 540 degrees. Okay. You also need to be able to go backwards, right? If you're given the sum, all right, then how many sides are there? Okay, so this is a setup of you set the formula equal to 900 in this case for number 6, right? Because that's the sum of the angle measures, all right? And so you solve for n, right? This is a heptagon, okay? Quick note here, in any polygon, the interior and exterior angles are always supplementary, right? Because it's a linear pair, right? Okay. And that's important. And if you look at the blank notes, there are actually 6 examples above this theorem, okay? It's another like discovery thing. The sum of the exterior angles of any polygon is always 360. All right, it's always 360, right? And so I know that we have these arrows here, but if you can see this pentagon without the arrows, right? The arrows just indicate if you were to extend those sides, right? So angle 1 is on the outside, angle 2 is on the outside, 3, 4, and 5. And so if you add those angles, it's always going to be 360 no matter what, okay? No matter how many sides there are. And so here, find the measure of one exterior angle of each regular polygon. So 360 because, again, the sum of all of the outer angles is 360 divided by 7 because there are 7 angles. All right, so each exterior angle is 51.4. All right. And so here's a quick problem here for find the variables for each regular polygon, right? Here, this is the pentagon, so 360 divided by 5 is 72. That's angle B, all right? And so then 180 minus 72 is 108, right? And if this is 108, then angle A is 108 because, again, if it's a regular polygon, all of the angles are congruent, equiangular. This is a four-sided figure, okay? Again, these are all exterior angles, right? If I try to highlight, right, this side here, sorry, this is terrible tracing, okay, right here, okay, if these are the sides, right, then each of these angles are the exterior angles, so if we add them up, it equals to 360. And again, being able to go backwards, all right? If you're given the measure of one exterior angle, okay, find the measure of an interior angle, then find the number of sides. And so if this is on the outside, right, so then on the inside, remember the inside and outside are supplementary, and so therefore one interior angle is 162 degrees, all right? And then we have this setup here. Remember, all of the for any polygon, right? The exterior angles add up to 360. And so if 18 is one exterior angle, then 360 divided by n is going to be 18 because n represents the number of sides, right? And so in this case, there are 20 sides. Okay, we can cross multiply if you want. And if you think about it, 360 divided by 20 sides, a 20-sided figure is going to be 18 degrees each on the outside of that figure, all right? Okay, and we do the same here for number 13 if an exterior angle is 12, all right? If you have any questions, please shoot me an email. Hopefully it was clear. Yeah, let me know.